Everybody. We're going to start this research track with 3 talks, and we're going to invite first Matt, who managed the team.operator.com and .NET and the ANJ root servers infrastructure, alongside with Dwayne, who focused on data analysis and visualization and the root zone in his role with VeriSign. So we welcome both.
Thanks, Mauricio. So the timing of the coffee break worked out well. We had a biohazard team come in here and sanitize the podium after Casey's talk. So I can say that I work with him. So we're here to talk about the attacks against the root on November and December 2015. Just a disclaimer, this is from VeriSign's perspective. We're not speaking for any other root operators, but we're here to talk about what our observations were of the attack. So there was a lot of discussion about the attack in the blogosphere. People were talking about it. People in this room were talking a lot about it. You might have seen headlines like this from the Register asking who was testing the DNS system. Hacker News talked about how many queries per second we saw during the attack. And the International Business Times wondered if ISIS was trying to destroy the internet. And then breaking news, we got outscooped by reporters on our own presentation. So if you just want to put your heads down and read about the articles, you can just read these 2 articles here that basically took our slides and talked about what we're going to speak to here. So there were 2 attack events. The first one was on November 30th. It lasted a little over 2.5 hours. And the second attack was on December 1st, which was just under an hour. 10 out of 13 root servers received attack traffic. Well, actually, it was 12. One question was, why did D, L, and M not appear to get attacked? We actually spoke to our colleagues at DRoot, which is University of Maryland. They renumbered their v4 address about 2 years ago. And the bad guys were sending traffic to the net block of the old IP address. So while they received the inbound traffic, it was black holed, and it probably just caused some problems for some of the college students trying to watch Netflix. LRoot was renumbered, Terry, 7, 8 years ago, roundabouts. They were sending traffic to LRoot's old IP as well, but it's not routable, so it didn't go anywhere. MRoot, which is the wide project in Japan, they were not part of the attack. And how do we know this, by the way, and we'll talk about this a little bit more, is we actually saw command and control statements from a botnet, and we saw which IP addresses they were targeting. The attack patterns were more or less identical across all the root operators. It was v4 traffic only, it was UDP traffic only. So the first attack was November 30th. All the queries were for www.336901.com. We believe that to be a Chinese gaming site. Again, the attack was about 2.5 hours long. Both A and J root received about 5.2, 5.3 million queries per second. You can see the ramp up was sudden. The amount of traffic was about pretty steady during the whole attack, and then it just dropped off. The second attack was about 24 hours later. I had just recovered from the first attack, and my sleep schedule was trying to recover, and then I was woken up again. For this one was a little less than an hour. And again, it was about 5 million queries per second. As my 9-year-old daughter said when she saw me walking around the next morning, "Daddy, did you get attacked again at work?" So, some more details. There were actually 895 million unique IP addresses that hit A and J root. So that's 20-some% of the v4 address space. Obviously, it was spoofed. About 4,700 IPs sent 100 or more queries. So, and then the top 200 IPs accounted for 68% of all the traffic that we received. And so you can also see that about 86% of the traffic was from 4,700 IPs. So the point is that while we had 895 million unique IPs, the majority of the traffic came from a smaller subset of IPs. So what was the impact? This is actually a graph from RIPE's DNS-Mon tool. If you're not familiar with it, the horizontal bars each depict either v4 or v6 traffic or impact, I guess you could say, per root letter. So can I use the mouse here? I guess I can't. No, it doesn't work. Anyways, most of the root letters had some kind of impact. A did not get any impact. We talked about D, we talked about L, and we talked about M and why they didn't have any impact either. So for A root specifically, A root's hosted out of 5 of our larger sites in New York, LA, Hong Kong, London, and Frankfurt. As luck would have it, Frankfurt happened to be out for maintenance during that time. No one alerted us about the attack coming. And so we were actually running out of only 4 anycasted locations during the attack. There was no measurable loss to A root itself. You can see I did a little pie chart here with the distribution of traffic per site. It's somewhat even. London got a little bit more, but that's where all the attack traffic went for A root itself. J root is different. J root is actually 12 of our larger sites and then lots of our regional sites. We have these small single server regional servers that are located all around the world. We have about 90 or so. And some of those sites did have impact mainly because of either upstream bandwidth limitations or just resource problems with a single server solution. So yeah, and by the way, small plug, if you're interested in hosting a JRoot node, talk to me afterwards. The JRoot traffic distribution, the top 5 large sites that received traffic were London, San Francisco, our Ashburn facility, Amsterdam, and Chicago, some of our well-peered locations. And our top 5 regional sites, those are the smaller servers, were in those 5 locations there. So what was the impact to our sleep schedule? We had a funny meme here that we wanted to show you, but our lawyer said it had copyrighted information, so we couldn't show it. So now I get to make fun of the lawyers instead of the image on the deck. So what did we do about it? So RL, we do have RL enabled on some, not all, of our name servers. It's most often deployed in our regional sites, the smaller sites. The good thing about RL is right out the bat it just worked, right? 60% of the attack traffic was often dropped at some of our locations. So there was no manual thing we had to do to make it work. And it was a good case of RL. However, there are limitations. It doesn't stop all the traffic. And it had some limited effectiveness for regions where they had low traffic volumes. So we have to, you have to trip that rate limit for it to start working, and we never hit that rate limit for some of our sites as well. Now the signature of the attack was very easily filterable. And so we looked into filtering the traffic, kind of similar to what Anand said in his presentation yesterday, where basically we could very easily inspect the packet and drop it in the kernel. So we ended up doing that. It was great satisfaction to hit the enter key and see all that response traffic stop. And it was very effective in stopping this attack traffic. It's also good because it didn't stop legitimate traffic for those domains either, because that wouldn't have been filtered. But there are limitations. It is manual for us, at least right now. It requires a non-trivial amount of DNS knowledge to craft the filter and implement it. And of course, there's always that non-zero risk of unintended consequences. We don't want to do something that affects root traffic at large. So this graph here depicts one of our regional sites in Geneva, Switzerland. This site did have RRL enabled. You can see when the attack started, the green line depicts inbound traffic, queries per second, and the blue line represents our response traffic. You can see the gap between the green and the blue line. That represents basically RRL working. So the number of responses that we were sending was much less than the number of queries that we were receiving. When we implemented the filter around 5:45 UTC, you can see that our response traffic dropped to almost, well, normal levels, which in this scale you can barely see. So this is just a good representation of RRL and how it helped us, and then how the filter helped us as well. So I'm going to hand it over here to Dwayne, who's going to talk a little bit more about the attack itself.
Thanks, Matt. So we were able to do some pretty nice visualizations of this data because we have this system we call response summaries that we store in Apache Avro, and we can do a query like you see here on the screen, kind of like an SQL query, and get a list of all the IP addresses involved in the attack. So this says, you know, give me the timestamp and the source address for this day, month, and year, where the destination address is ARoot and the query name is this. And this ended up being, you know, quite a large list of addresses, and we fed some of those into this visualization tool. So some of you may have seen this before, but this visualization uses a Hilbert curve to represent the IPv4 address space. It's a space-filling curve, and you can see an example of it here. It's great for doing this because it preserves address adjacency at any scale, whether you zoom in or out. So I'm going to attempt to play a video here. If people are watching remotely, you might want to click on this YouTube link. It's also in the materials on the DNS Oarc site. Should have this loaded up here. I don't know if the
visualization of anomalous traffic sound.
So here's the Hilbert curve. The big rectangle. I don't think I have. Oh, I do have a pointer. So the big square represents the whole address space, and then it's divided into these smaller squares. There's a number in each square which represents the first octet. Oh, thanks. The first octet of the address space. So in this video, there's some audio where I'm explaining what's going on, and in a second it should pop up with some data. Each dot on the screen is representing a /16 of address space, and the color of the dot indicates how many queries were received with an address in that /16. Blue is low query volumes, and red is high query volumes. This was a 5-minute YouTube video, so I may have gotten a little bit ahead of the narration here. I have to wait for it to catch up. So at this point, it's paused, and this is showing only the first 500,000 queries in the attack, and you see that this half of the space is filled with sort of blue colors. There's some gaps. There's 0/8, 10/8, and 127/8 didn't receive any traffic, and that's because those get filtered before they hit our servers, and we don't log those. You also see that there's this little thing sticking out. That's 128/8, and so it's sort of my opinion that, you know, the intention of this attack was to source queries from the first half of the address space, but they have like some kind of off by one error, and they went just a little bit too far maybe. And they're also sourcing queries from 128/8. So now you see this, hopefully you see this red activity up in the top corner there. And you see it sort of wandering around, and that's following the path of the Hilbert curve. So this tells us that the source addresses are being generated sequentially. And you can see it wandering through the space there. And you can also see, again, now it's paused. This is something like the first 2 million queries, I think. Or maybe it's 20 million. But you see the different areas. There's the red area, which represents, you know, very high rate queries. There's a large green, which represents sort of mid-level query rates, and there's a little bit of blue, which represents low query rates. So this sort of tells us that there's different processes or different algorithms at play here, sending queries from different addresses at different rates. So using this tool, I've just reset the counts and zooming in on this so you can sort of better see how it traverses through the address space sequentially. And you can also see that there are sort of two. Now there's two, in the video I call them attack fronts. There's two things crawling through the space. One of them, the one in front, seems to be going at about twice the speed of the one in the back. And then pretty soon here, the video pauses before it reaches the 10 net space. And the reason is because, if you sort of watch it, you'll see that it finishes with 9, and then you don't see anything for about the length of time that it would take to fill the 10 space, and then it proceeds on to 11. So, that kind of tells us that this attack code is generating queries for RFC 1918 address space, and they're being sent over the network, but they're not making it all the way to our servers. If I was brave, I would fast forward a little bit, but. So by the way, this tool is now available as open source. I'll have the URL in a couple of slides. It's free for you to download and try it for yourself. So what happens next is this, I don't have a pointer, but it's gonna, this number 19 up here in the top right corner, when the sort of attack gets to that phase, you'll see that it stops and restarts back over at 2 where it started before. So for this high rate, this red area, this very high rate of queries, the attack just looped through that. It cycled through. It never really went past the 19 net address space. So I think we're getting low on time, so I'm going to stop this and go back to the slides, which are where? This one? Yeah. How do I go to full screen? Somebody tell me what to press for full screen on Keynote. Ah, okay. So some of this I already talked about, the takeaways. There's different processes, there's different rates of queries going on here. There seems to be a small number of very high rate sources. And after we published this video, some security experts were still not convinced that, for example, that the source addresses were spoofed. There's a quote here from John McAfee disagreeing with our conclusions, and you can read that further in the article linked down there at the bottom if you're interested. As I said, this software, it's called GL Heatmap. It's on GitHub. You can try it out. You can email me questions because there's very little documentation about it. So in that video, we sort of focused a lot on the left side of the address space and the areas that get filled in a lot. But there was actually some other things going on the other side that we didn't really talk about in the video. There was a small number of points that had sort of also high rates of queries. And to sort of further explore that, we make graphs like this, which show the distribution of query counts ranked by source address. There's 2 lines here for the 2 different days, November 30th and December 1st. And they're a little bit different because the attacks were different durations. But the fact that this curve sort of has this sharp bend down here is an indication to us that there are different things going on. And as we zoom in farther, so in this first graph, the y-axis goes from 0 to 5,000. This is 0 to 10. And this is 0 to 0.1 queries per second. And you can see there's this very sharp sort of cutoff down here. Again, to us, that's evidence that there's different processes at play here. This is another way to look at that same data. This is a sort of a scatter plot. Here, the x-axis is the first octet of the sources, and we see there's sort of different groupings here. It is our opinion that this circled section here are the spoofed addresses, and this other section is maybe something else going on, such as packets that get intercepted and diverted to NATs, which might expose real IP addresses or something like that. Here's a list of the top 20 source IP addresses by their autonomous system number. The point here is just to say that we don't believe that there was a single that the sources were chosen to do harm to some victim because the spoof sources were sort of distributed everywhere across the globe, right? So as Matt alluded to, our security research colleagues observed the command and control instructions for this botnet that correspond to the same time and parameters of the attack. And they were able to link it to some known malware that's sometimes referred to as Bill Gates or Web Tools. I think it has some other names as well. And that malware is known for being able to generate DNS attacks just like this one. So a lot of questions about, what's going on here, why are people doing this, what is the motivation? There was speculation that the motivation was to do harm to the root server system. We believe that the choice of the query name doesn't really support that motivation. And as Matt said also, there were some root server letters that didn't receive any traffic. Perhaps the intention was to harm these two particular domain names that were used in the attack. I say perhaps, but the response packets were not directed towards them. So perhaps the intention was to deny service of those domain names to make it so that they did not resolve. Also willing to consider other ideas that this was someone just showing off or someone doing some beta testing of new attack methods, or maybe even creating a diversion for some other attack that might have gone on at the same time. We happened to notice that the day after that second attack that the .com name servers were receiving attack traffic with the same query name, the 916yy.com. So I guess I don't have a pointer, but under the November 30th, there's this yellow peak, and that's actually December 2nd. That's the attack that received at the .com name servers. And you can see that it's not the first time that similar attacks had been going on earlier. We just never noticed them because we never really had a reason to look for this particular name before. So wrapping up, we feel that RL did a pretty good job as a first line of defense for this attack, but filtering was really necessary to squash it entirely. It was large enough to affect a number of root server letters. Of course, not all letters received the attack traffic. The source addresses were certainly spoofed, and we think that the intention was to disrupt the resolution of those two particular domain names and not necessarily do harm to the root system itself. So I don't know exactly how much time we have for questions. About 5 minutes.
Jeff Houston, APNIC. You mentioned that there were sort of two classes of IP addresses. One is this spoofing that sort of no single IP address sends you many queries at all. And the second set, where you're getting this intense amount of activity from a small number of IP addresses.
Right.
My assumption is, and correct me if you're wrong, that RRL hit the second set but not the first. And was the attack one that was evenly smeared across the space, RRL would have actually been ineffectual in that particular situation?
That's probably fair, yeah.
Okay.
Yeah, RL didn't trip unless it was getting a certain query rate, and that was not seen
From
at
the
all.
same source address?
That's
so
correct, from the same source address, and not all of our regional sites were even well connected enough to see some of that attack traffic. So yes.
Thanks.
Robert Edmonds, Farside Security. Your last slide here, we believe that the root itself was not the intended target. Do you have any thoughts on why they attacked the root in the first place, if they were trying to take down these second level or third level domains?
Sure, so, speculating quite a bit, I think that
Yes, please.
the idea is to target these particular domains, and as attackers, they have a number of tools at their disposal, or maybe they have a number of attack providers at their disposal, and so they're sort of trying all the tricks that they can think of, and this is perhaps one of them. One of their tricks is to send these queries to the root servers. Another trick is to send such queries to the .com name servers, right? So I think they're just trying whatever they can.
Right. I've noticed sometimes even experienced technical users, maybe not DNS specialists though, will sometimes confuse root server and TLD server.
For sure, yeah.
Like they'll say, we'll refer to the COM servers as the root servers, right?
Right.
So is it perhaps better user education about the DNS would help these cyber criminals to attack the right servers?
Yeah, I think you should draft a document like that for DNS-Op.
Alfred Benomdum. Was there any kind of evidence of it being purely botnet, or was there also some kind of reflection, meaning open resolvers involved in it?
So I guess we didn't really go looking for open resolvers in the data set. So I don't really know the answer to that. I think we, like I said in that video, we sort of focused a little bit on just the spoof sources. But it's possible that one of the other tricks in their tool bag would be to use open resolvers, and maybe that was in there also.
Giovanni Moda, SIDN. What about BGP and Anycast? Even though if these IPs were actually spoofed, you could assume more or less that the prefixes that they come from, the instances that are more attacked, the Anycast nodes that are more attacked, would give a hint where those IPs were actually originated. Did you guys take a look at that and like individual Anycast instances or sites?
There was a decent amount of traffic that hit our sites in Asia. So one could possibly link those two.
Yeah, thanks.
But not only Asia.
Yeah. And also, I mean, London was at the top of some of those, the pie chart and lists too, so, yeah.
Ola Gomes on Cloudflare. First of all, thanks for releasing the tool. Can you go back the slide that shows what you think the traffic was from, the one where you see the spoof traffic versus possibly natted traffic?
This one?
Yes, this one. This is very interesting.
Yeah.
How do you derive this?
How did I generate the graph?
No. So what it attributes the query rates? So you're looking here that like if we look at the 1,000 line, there are not too many hosts that are doing that.
Yeah.
So that is what you're expecting, that you have some bot behind a NAT, or?
Well, so one of the reasons that I'm saying this is because for the lower grouping here, it's all in the first half of the address space, and there's nothing in the second half, and so why would we see any queries from sources in the other half of the address space? And the theory is that maybe they got intercepted along their way, right, and their address got changed.
Okay.
So that's sort of where I derived that from. Does that answer your question?
Partially.
Yeah.
The second part of that question is, are any of these addresses represents the dots in the upper graph from your list of known resolvers?
Yes. Well, from known resolvers.
Yes.
We didn't check that actually, but certainly they were in the list. Yeah.
Okay.
Yeah.
Thank you.
Last question, please.
Hi, good morning, Joan. Pablo Carboni from Claro, Argentina. My question is a little question. How about bandwidth consumption? Big bandwidth?
So some of our regional sites have 1 gig pipes, and we got close to 1 gig on some of those locations. At our large sites, we have 17 what we call large sites. We didn't have an issue there just because of the amount of resources we have. I don't remember off the top of my head how much bandwidth it was, but it was in the order of many gigs.
Oh, terrible.
Yeah, so,
Thank you.
yep.
Hi, I'm Robert Martin Lechen from PCH. So the victim domain name or target domain name that was, well, the target, have you looked into what that actually provides? Is it a casino site or something? And actually, one of the addresses that would be in that zone, I mean, obviously you don't have the copy of their zone, would that be one of those dots?
So your first question, one of the sites resolved to a gaming site. I went to it. I don't speak Chinese, but it looked like a Chinese gaming site. The other one, when I checked it out, there was nothing there. And with regard to your second question, Dwayne, I'm going to let you answer that.
Yeah, I didn't look actually. I don't know.
It would be interesting because the query rate is quite high. So, yeah. I mean, if the website of that name would be one of those dots, as you said yourself, it could be a diversion, right?
Yeah,
or whatever.
For sure.
They're hiding it in there.
Yeah.
And the needle in the haystack. Okay.
Thank you.
Can I have one more? One more. Yeah. So, is it all right? Thanks. So I think the overall conclusion here is this is pretty reliable. I mean, the root service were not taking down any RJ, but mostly performance degradation in some sites. Can you conclude that from those?
Was the root system okay as a
So A and J.
Is your question, was the root system okay as a whole?
Oh, A and J, because I understand you cannot speak.
Specifically A and J, A had no impact. And J, the impact was to the small regional sites. Any traffic that went to our larger sites was not impacted either.
All right, thanks.
One question from the Jabber channel. This is from Peter Lexis at Power DNS. Do you have a measurement from which upstream networks the spoofed packets came from, i.e. based on packet TTL, where they originated?
We didn't do that. No, I'm sorry, we didn't do that.
Thank you, guys.
So I would like to introduce Roy Arends. He works as a principal research scientist from ICANN.
Hi everyone, just like Mauricio said, I'm Roy Arends. My job title is Principal Research Scientist. Now, Principal, Research Scientist? I mean, I hope to get 1 out of 3 right, while I'm waiting for the slides. There we are. Perfect, so this presentation is about DNSSEC key tags. Who knows what key tags are? DNSSEC key tags. Oh, great. That's a nice quorum for a DNS Pubquiz. So at ICANN, sometimes I present the DNSSEC Pubquiz, and I always have these questions, these multiple choice questions. So here's one, right? What is a DNSSEC key tag? Is it A 16-bit value in the DNS key R data? Raise your hand if you think that's it. Okay. A physical tag that you'd hang on your keyring. Very good. C, a 16-bit value in the DS and RRSIC data. Yes, perfect. It is C. I'm not going to ask if you think it's D. Okay, D, a special variation in the game of tag. Brilliant. Thank you, guys. Thank you for playing along. Now, the reason I looked into this is, as you probably have learned or heard by now, there's a design group around the KSK key realm, and I'm part of that group and a design team. And I was building my own testbed to get some experience with it, and this is to roll the KSK that was introduced in 2010. And when I started doing this, it was in 2015, last year. Now, the problem is I don't actually have access to the real DNSSEC root keys. That's not a problem. It's a challenge. Yeah? And so I decided to generate my own, so I thought I could be like Warren Kumari and be all cute and have my own key tags. And so the key tags would then be 2010 and 2015. The only problem with that is you can't just assign a key tag to a key, right? RC 4034 says the algorithm for calculating the key tag is almost, but not completely identical to the familiar once complement checksum used in many other internet protocols. Now the part that says almost, but not completely identical will come back later, so keep that in mind. So a simple trick, and you've probably all done this before. While true, do DNSSEC keygen, right? Have a loop and make some coffee, and a few hours later you break the loop and you count the amount of keys. But I only generated 16,000 keys, right? 16K keys. And I was expecting 64K. The reason I expected 64K, the field is 16 bits wide, and another problem is key tags 2010 and 2015 were absent. Now, I went to DNS Operations. I mean, I I just didn't know what to think. So I went to DNS-Operations, and Dwayne, who was just up here, he basically said, you know what? I think it's this. When you use DNSSEC keygen, the tool actually checks on disk if the key tag if you're about to write, right, already exists in terms of the same key tag. If it does exist, it won't write it. Now, what I call a Mark Andrewism, hi Mark, what it also does is it sets the revoke bit of the key, it then regenerates the key tag, right? When you set the revoke bit, you need to regenerate the key tag because it will be different. And also it will also check if that exists on disk. Now, not only that, it will take the list of key tags on disk and it will generate the version that has a revoke bit. And it will then check if the key you're about to write matches that. So that cuts the space in half, right, and in half again. So it would be 25%. Nice, great, well observed, so perfect, we now have a solution. The reason I call this a Mark Andrewism is like first you think like, what the, right? And then you think like, that's a really, 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 really good idea, right? And then you find it's not documented. No, but I'm not sure, sorry Mark, I don't want to call you out. I'm not sure if you actually did this or someone else, but... I'm sorry? It was actually me. Oh, Evan, sorry. We have an huntism. Okay. Anyway, so I still needed my key tags. So I simply did the same thing. After I wrote the key, I removed the key, right? And I just want to make sure I can get to that 64K. And when I did that, I get 16387 keys. So this wasn't the issue that Dwayne pointed out, but strangely, I didn't get like a nice hexadecimal round number, like 4,000, which is hexadecimal for 16384. I got 16387, which is weirder than what I expected, which is already weird what I expected. Anyway, so it must be the tool. I decided some other tool, which is LDNS keygen, and which is nice and simple, no undocumented features, I think, at least not that one, and it will allow you to shoot yourself in the foot. So I did that, counted the amount of private keys that I just generated on disk, and the result is 16385. Again, not enough key tags, two issues here, not enough key tags, I expected 64K, but also an off by one error. Anyway. So meanwhile, via Twitter, Peter van Dijk, he wrote, just as a data point, I now have a collection of 2K keys with 17896 distinct key tags, still generating more keys. Now, I don't tweet that often, but I replied to him, so dude, what tool are you using? And his response was, I'm using pDNSSEC add zone key. Now, pDNSSEC is a tool from PowerDNS, and that's where Peter van Dijk works. And they're using a different library. They're using embed TLS 2.1.0. So I'm like, it's not the tool, right? It's definitely not the user. So it must be the library, right? So here's one library that generates half of the keys compared to the other library. So there must be something funky going. Is this a bug in OpenSSL? Sorry, I'm so used to saying OpenDNSSEC. If this is a bug in OpenSSL, so, I mean, I'm thinking, you know, Heartbleed, I already start registering names, call the marketing department from ICANN, etc., etc. But meanwhile, Peter van Dijk, now on DNS-Operations, says, I now have 130,000 different keys with 32,000 unique key tags. Now, this is almost twice as much as Roy, not that we're competing or anything, but it looks like it might top off around 32K. So, still not 64K. And then he says on Twitter, I now have 32769, yes, 9, right, key tags. Also the same problem, this off by one error. So now what? We've got 3 different tools, we got 2 different libraries and 3 issues. Not enough key tags, off by a few key tags, and one library produces less than the other. So while we're digging into this, right, it gets more and more mysterious, in my mind at least. So naturally, you go, you try to look further and further. What's the common thing about all of these tools, right? Which is, it's the key tag function. So I had this little loop that will basically generate, so if you see jot-r on the screen, yeah. So what jot does is basically generates a range of numbers, and -r means randomize them. 128 means create 128 values, and from 0 to 64535 inclusive, that means basically a 16-bit word. And then this is my own version of the internet header checksum. It's very simple, very straightforward. You basically add all of these bytes together and you do it modulo 64535, right? And the result, you put in a file called test, and you count and unique the test file, and you get a fantastic number, 64536 unique key tags. What I'm trying to say with that is, it's not the function. I mean, the function is broken in a way, but it's not the function that generates lesser key tags. So it's not a key tag function, it's not a library, it's not the tools, and definitely, okay, hopefully not the user. So I'm lost here. I have no idea what to do next. So I'm checking DNS-Operations, right, and Twitter, nothing, radio silence. And I'm still completely mystified. And meanwhile, I can't get my vanity key tags, right? So in comes Florian, Maury, and Jérome Plut. I didn't know these people before, but since then they've helped a lot in trying to understand what's going on. And it turns out the internet header checksum, and it's going to get very, very complex, at least for me. This is modular arithmetic, and I can't even add 2 and 2. So if the internet header checksum is equivalent to addition modulo 64535. And I try to explain that here. So you basically have a 32-bit number, right? And if you do the internet header checksum, you want to add the top 16-bit to the lower 16-bit. Now, when you do that, you have some carry as well. And if there's no carry, so if the top 16-bit and the lower 16-bit combined, right, if you add them up and they are lower than 64535, you have no carry bit, right? There's no carry because they're lower than 64535 inclusive. And so you can see that that already works. That's not on the screen, that already works. Now, if you do, okay, sorry, this is getting way too complex really quick and I don't have much time. Just trust me that the internet header checksum is equivalent to num, the value, right, modulo 64535. During the coffee break I can explain the math. So in our case, the value, that num, $num, contains the R data of the DNS key. And the R data has a constant part for all these keys that I generated, right? The RD stuff, RD length, protocol, algorithm, exponent, etc., etc., etc. So that I call the constant part. And it also contains the RSA modulus, right? And that's the stuff that's varying through all of these millions and millions of keys I generated. And the modulus is basically nothing else than a multiplication of 2 very large prime numbers, P and Q. So we have value modulo 64535, which is equivalent to constant plus P and Q, modulo 64535. Now the modular arithmetic is transitive, so you can do it on the individual parts here. You basically have constant modulo 64535, and you have P times Q modulo 64535. Now, the constant, in our case, modulo 64535, would result in 1803. It's not on the screen, forget it immediately, but that's 1803. It would be constant all the way through. So the problem must be in the second part, P times Q modulo 64535. So if you understand modular arithmetic, right, you need to know that 64535 is composed of 4 prime factors, 3, 5, 17, and 257. And all of these numbers, P, Q, 3, 5, 17, 257, they are all co-prime to each other. I mean, none of them are divisible by another. So if P and Q can be divided by 3, 5, 17, and 257, that means if you do this big number, modulo, let's say 3, the result can never be 0. If something modulo 3 is 0, it means it can be divided by 3. Or if something modulo 5 is 0, it can be divided by 5. Sorry, it is divisible by 5. And if something modulo 257 is 0, right, that means it's divisible by 257. And so you know that this will never be the case, because these are very large prime numbers. Right? They're not composed of these of these vectors 3, 5, 17, and 257. So we can now make a list. P times Q modulo one of these vectors will never be 0. That means if you do P times Q modulo 3, you got 2 solutions and not 3, right? Remember, 0 doesn't happen as a solution, only 1 and 2. The same goes for 5, it has 4 solutions, and 17 has 16 solutions, 257 has 256 solutions. And if you multiply all of these things together, you get a magic number of 32768 different key tags. So it's not possible to get more key tags than 32768. So of the 3 issues, we have now 1 solved. We don't have enough key tags. We now know why. I have to say that insight of these guys was absolutely brilliant. I've never known this before. I know there was issues with the key tag function calculation, that it wasn't the same as the internet header checksum, but almost. I know there are issues there, but I never ever thought that modular arithmetic and key tags would cause a reduction in the namespace, in the key space. Anyway, we still have 2 other issues, off by a few key tags, and one library produces half of the other library. Sorry, that's Jared. That's 5 minutes. Oh, sorry. 3. I'll be really quick. So we're still off by a few. And remember, I said very similar, but not exactly the same on the key tag function. So the difference between the internet header checksum and the key tag function is the following. So you have the accumulate. So this is the RC34 key tag function. The first line adds, it basically adds stuff to each other. And the second line assumes that there's no carry, right? But if the accumulator already is a large number, and what you add to it will bring it over 64535, that means you have a carry, the value is larger than 64535, and that carry value is now ignored because you do AND 64535 and FFFF. And that's the difference between the key tag function and the internet header checksum. And as a result of that, you get a few off values. So let's say you have 128 bytes that you add together, right, or 128 words that you add together for 2K key. That means you have 127 possible different carries going on. So that means for a 2K key, you can possibly have 127 more key tags than you would expect. So 32768 plus 127 for 2K key. Anyway, then we have one more issue unsolved, right? One library produces less than the other library. Now Peter is using embed TLS, and I'm using OpenSSL. It turns out that OpenSSL only generates safe primes. It doesn't mean that embed TLS has unsafe primes, but the idea is basically a safe prime is a prime. If you take one off and you divide by 2, if that number is still prime, it's called a safe prime. And this implies, if you do the arithmetic here, this implies that P mod 3 will never be 1. We already know that P mod 3 will never be 0, right? If that's the case, it would be divisible by 3. But P mod 3 is never 1. That's what a safe prime is, basically. And this is always 2. Now, since we're multiplying 2 numbers, P times Q, right, you basically get 2 times 2, the result of the modulo function 3, right? 2 times 2 is 4, 4 modulo 3 is 1. So P times Q will always be modulo 1. Always be, P times Q modulo 3 will always be 1. So if we go back to that list that I had before with 32768, now if we change this, we know that something P times Q modulo 3 will always be 1, right? We only have one solution. So instead of 2 times 4 times 16 times 256, you do 1 times 4 times 16, 256. You get 16384 key tags. So, 3 issues, 2 solved. That actually should read 3 issues, 3 solved. That's what you get when you copy the slides. Anyway, this was my little endeavor in trying to find out why all these key tags were missing. But the real work has been done by these guys. So it was Warren Kumari who helped me out with all the tools. Ben Laurie from OpenSSL that immediately said, no, Roy, it's not OpenSSL. It can't be OpenSSL. And Florian, Maury, and Jérome Plut, who actually explained the math behind it. It was Jean-René Reinhardt. Also, these 3 guys that I just called out, they work at the same company. he actually explained the math between for the safe primes and the non-safe primes. Peter van Dijk and Bert Hubert, of course, from PowerDNS, they helped me test with their libraries and got those interesting results. And David Conrad, so I wrote a paper out of this, from this, and David Conrad changed the Dutch English into proper readable stuff. So, and of course, all of you who have participated in the DNS operations discussions and on Twitter on this. So I hope this was useful. If you have any questions, let me know. Hopefully not that much math questions, because I'm not that good in it. And if not, going, gone. Thank you.
Okay, and for the last talk of this segment, we invite again Dwayne Wessels, who will talk about CSK size changing for the root zone.
Yes, hello again, everyone. Thank you. So this talk is about VeriSign's plan for increasing the zone signing key size for the root zone. Here's a brief outline. I'm going to talk about the current root zone DNSSEC parameters, and I'll say a little bit about the schedule for increasing the ZSK size, provide some details on how the change will go, have some data on consequences of a 2048-bit ZSK, and then talk a little bit about fallback plans. So here's some initialisms that are used throughout this presentation. If you don't already know, KSK is key signing key, and for the root zone that is operated by IANA/ICANN. ZSK is the zone signing key, and for the root zone that is operated by VeriSign. KSR stands for key signing request. This is a bundle of ZSKs in XML format that VeriSign transmits to ICANN to be signed at one of the quarterly key signing ceremonies. And just to be super confusing, SKR is the response to that. It is the bundle of signatures over those keys that we get back. So you may have heard talk recently about KSK rollover, and that is not what this talk is about. I think we'll hear more about the KSK rollover in the afternoon. And for anyone who loses sleep at night worrying that somehow a ZSK change and a KSK change may collide in time and cause response sizes to blow up, I am here to assure you that we're working closely with root zone management partners to make sure that something like that never happens. So here's the current DNSSEC root zone parameters. The algorithm is 8, also known as RSA SHA-256. KSK size is 2048, ZSK is 1024. The KSK has never been rolled, although if you're a fan of the DERs, you may disagree with that. The ZSK is rolled every quarter, every 90 days. KSK has a resign period of 10 days. The ZSK is 12 hours. KSK has signature validity period of 15 days. ZSK is 10 days. And obviously the KSK signs DNS key records, and the ZSK signs everything else. So the plan is to increase the ZSK size to 2048 bits, but no other parameters will be changed. Briefly, here is the schedule. Later this month, later April, testing will begin between ICANN and VeriSign with key exchange servers and so on. In mid-May, KSK ceremony number 25 is where the Q3 ZSKs will be signed. In August, the next ceremony, the Q4 ZSKs will be signed. September 21st is the first date at which the 2048-bit ZSK would be pre-published in the root zone. And on October 1st, which is the start of the fourth quarter, is the first day that the root zone would be signed with a 2048-bit ZSK. And this shows that graphically. Here we have these, I don't have a pointer again, but the blobs at the top are the KSK ceremonies, and they point to the published keys that happen the following quarter. So there's an interesting bit that I want to focus on down here between the end of Q3 and the start of Q4. The dark blue represents the 2048-bit ZSK, which gets pre-published right at the end of Q3, and that signature needs to be generated in Q2 at the light blue ceremony, which is sort of off the screen here. So some more details. As I said already, the ZSK is rolled every quarter. Each quarter is divided into 9 slots of 10 days each, although for some quarters the last slot is a little bit longer to accommodate the duration of the quarter, either 10 or 11 days. The DNS key RSIG record changes in each 10-day slot. We obviously use a pre-published technique for the root zone, so incoming ZSKs are pre-published for 1 slot, that is the 9th slot of a quarter, and the outgoing ZSKs are post-published for 1 slot in the 1st slot of a quarter. And as it would happen, we are today at the start of a new quarter, and so if you were to do some digs and whatnot, you would see that there are in fact 2 DNS key records in the root zone, 2 ZSKs published in the root zone right now. And during those slots, during the 9th and the 1st slot, the size of the DNS key response message is increased due to the fact that they're being post-published and pre-published. So this depicts that sort of graphically. At the top, we've got a quarter where in the blue, you've got, and so I should say this also shows the way things have been going to date with a rollover from a 1024-bit to another 1024-bit key. The blue boxes represent a certain 1024-bit key that's used for signing during that 1st quarter, and then there's a 1-slot post-publish period. The green one, the green key, is pre-published in slot 9, and it proceeds on and on and on. So during those 2 slots, slot 9 and slot 1, the response size increases a little bit. And this diagram shows what will happen when we change the size to 2048 bits. So the blue here is a 1024-bit key, and the green is a 2048-bit key, and the red is another 2048-bit key. The only thing that's different from the previous graph is in the quarter when we start signing with the 2048-bit key, we will have a longer post-publish period for the outgoing 1024-bit key. So whereas normally it's post-published for 1 slot, 10 days, we'll instead post-publish that for 3 slots or 30 days. That's saying the same thing. So let's say a little bit about the consequences of what it means to have a 2048-bit ZSK in the root zone. This chart, this graphic shows the size of assigned DNS key response at various phases throughout the process. These colored boxes represent different parts of a DNS response. The first small one is the header and the question section, and then these bigger blobs are, the first big blob is a KSK, and then there's a signature, and then there's a blue ZSK. And during a normal operations, not during a rollover, but normally for a 1024-bit ZSK, the size of the DNS key response is 736 bytes. And if you were, again, to do a query today, you would see the second line. You would see that there's 1 KSK, 1 signature, and 2 ZSKs, and the response should be 883 bytes. When we do a transition from 1024 to 2048-bit ZSK roll, the response size will be 1,011 bytes. And then at the end of the post-publish period, it will go down to 864. And then when we do a 2048 to 2048-bit roll, it'll be 1139 bytes. So even though I told you I wasn't going to talk about KSK rollover, here's a little bit of data on what things would look like during a KSK rollover with a 2048-bit ZSK. During the KSK rollover, the DNS key response will again be 1139 bytes, and should there be a published revoke of the old KSK, in that case we have 2 KSKs, 2 signature records, and 1 ZSK, and the response size would be 1425 bytes, which is getting kind of close to the size of an unfragmented IPv4 UDP message. So that was all about DNS key responses, and we're also interested in the impacts on other types of responses because those are much more common. Again, all non-DNS key R sets are signed by the ZSK, and those signed responses will get larger. A signature record for a 1024-bit ZSK is 159 octets, and for 2048 bits, it's 287 octets. That doesn't tell the whole story because the queries that come in have different parameters. Not all of them are requesting DNSSEC, and some of them will have different advertised buffer sizes and so on. So to understand this better, we did a little simulation, took some query logs and replayed them through various signed zone configurations. So I captured 10 minutes of queries sent to a route and generated a number of zones signed in different ways, and then replayed the traffic to all those, to name servers serving those zones, and recorded the response size and whether there was a TC flag set and so on. So this data comes from February 24th. It was a 10-minute trace with 41 million IP packets and 37.5 million UDP queries captured from our 5 A-route sites listed there. I bet this is impossibly small to read up there, but these graphs are going to show the different zone configurations. And the first one is the normal 1024-bit zone during a non-rollover time, then 1024 to 1024 rollover in dark green. In red, there's 1024 to 2048-bit pre-publish phase, followed by the same in the post-publish phase, and then some blue areas for 2048-bit normal operations, followed by 2048 to 2048-bit rollover. But when we look at fragmentation, it's essentially 0 in these simulations. And the reason is because the only types of responses that get fragmented are any queries to the root zone. And in this particular trace data, there was very few of those. So essentially no fragmentation apart from the any queries. Truncation is a little bit different. The first green bar on the left here shows that during the normal 1024-bit operation, something like 2.5% of all of DNS key responses are truncated. And during a 1024 to 1024 rollover period, which is again happening today, something like 5 or 6% of DNS key responses get truncated. And it stays at that level for all of the other scenarios that were simulated. So again, that was just for DNS key responses, and here's how it looks for all responses overall. And here you can see that the level of truncation really depends on which key is used for signing. When we're signing with a 1024-bit key, the truncation level is something like 0.5%, and it will go up to like 1.4% when we start signing with a 2048-bit key. This graph shows the response size distribution for all those events. And again, this really only depends on which key is used for signing. So a lot of these lines are stacked on top of each other. And there's really only 2 cases. There's the red one, which you can see is for the 1024, and the blue for the 2048. And if you look sort of halfway up the y-axis, you can see that the median size for 1024 is something like 650 bytes. And for the 2048-bit ZSK, it's maybe 900 bytes. The story for bandwidth is sort of interesting, and this is something that root server operators need to think about. And again, it only depends on which key is used for signing. For 1024-bit keys, we might expect a typical root server letter to require something like 250 megabits per second of bandwidth. And when we switch to 2048-bit key, it'll jump up to like 350 megabits per second. So I'll talk a little bit about some fallback plans. Even though we fully expect this to go off without any incidents or problems, we need to be prepared for problems that may be beyond our control. So should it be absolutely necessary, we'll be prepared to revert to a known good state, which is a 1024-bit ZSK. And in fact, we will reuse the same 1024-bit ZSK from the previous quarter during the rollback, or during the fallback. So in order to make that happen, when we go to the KSK ceremonies, ICANN will sign 2 key signing requests at 2 of the ceremonies. One of those will contain the 2048-bit ZSK plus all the necessary pre-publish and post-publish keys. And there will be sort of a fallback KSR with just the 1024-bit ZSK and all the necessary post-publish and pre-publish keys. And here's how that might look if you displayed it graphically. The top section shows the 2048-bit ZSK proceeding normally, and down at the bottom we've got the 1024-bit fallback. So again, it will be the exact same key. 1024-bit key will be used in both Q3 and Q4. The sort of the green dashed boxes represent the 2 KSRs at the May ceremony, and the blue boxes here represent the 2 KSRs at the August ceremony that will be signed. Criteria for executing a fallback, there would have to be something unforeseen, something very serious, and something that can't be solved by temporarily disabling DNSSEC validation for someone. And as we think about fallbacks, here are some important milestones that we'll be watching very carefully. First is the time when the 2048-bit ZSK is pre-published. That's slot 9 of Q3. That's that September 21st date. The next is the date at which the zone is first signed, of course, with the 2048-bit ZSK, slot 1 of Q4. And it'll take a couple of days, of course, for cache signatures to expire and so on, so we'll watch that over that time period. And then the last big milestone is the removal of the old 2048-bit ZSK at the end of the post-publish period. That's the point of no return. At that point, we cannot go back to a 1024-bit ZSK easily. So should it be necessary to do a fallback in slot 9, all we need to do is unpublish the 2048-bit ZSK from the root zone and continue publishing only the current 1024-bit ZSK and keep signing with that key. And then there would be no ZSK rollover for the next quarter because, again, we're proposing to use the exact same key quarter to quarter. A slot 1 fallback would happen if there are problems that arise from generating signatures with the new ZSK. In that case, we can revert to signing with the old ZSK. It's still being published in the root zone. And if and when to remove, to unpublish the 2048-bit ZSK would depend on the nature and particulars of the problem that we experience. So that's it. Happy to take any questions at this time.
Dwayne.
Hello, George.
Dwayne, did you really say?
No, I did not.
Did you?
No.
Did I or did
No.
I not? Have you ever been? It sounded like you said if you could fix the problem by expecting all of the world to
I did not say all. I did not say all. No, I did not say all.
But you did say disabling DNSSEC fixed the problem, then it would not be a fallback situation. If you could fix the problem by disabling DNSSEC, it would not necessitate
Temporarily disabling DNSSEC validation, if yes, if
who has to do that disabling?
Who has to do it?
Everyone.
No, that's not what I'm saying.
Okay.
No,
thank
no,
you.
I'm saying if you know, company XYZ runs certain software that for whatever reason is not compatible with a 2048-bit ZSK, if they can solve that by disabling validation on their systems, you know, that's not good enough, that's not a sufficient reason for us to execute a fallback.
How about if there's a million company XYZs?
That's different, right? That's what it would have to be a very serious, unforeseen
Okay.
problem.
So
Yes.
it's about the volume of people who would have to do disabling of DNSSEC. That's the decision logic. If it's one company per, if it's a million, might be.
Yeah. If it's a systemic-wide problem with certain software that everyone in the world is relying on, right? That might be the
Okay.
kind of thing where we do a fallback. If it's this one,
Yeah.
maybe mid-sized company that's using software from 10 years ago that can be fixed by disabling temporarily until they can upgrade, we're not going to fall back for that company.
So I have a second question unrelated. I've never been to the key ceremony, but I like to imagine
You should go.
you have to line up and do the chicken dance facing east. And it's kind of highly scripted, right? There
Yes.
is a quite accurate check sheet that says you've got to undo the first button of the shirt before you put the arm out, and then so you're kind of going off-piste in this because you're saying we want to go into the room and do a ceremony where we do twice as many signings than we normally do. Is there a new magic recipe? Has someone pre-written the checklist for that new recipe? Because the magic counters in the HSMs are going to tick over twice as many this time. The input and exit conditions for this round of the ceremony don't match any other round of the ceremony.
Well, first of all, you should go to a ceremony. I think you would find it very entertaining. You could do the chicken dance. I think maybe I shouldn't speak on behalf of our colleagues from ICANN, but in my opinion, the actual signing part of the ceremony, it takes about a minute.
Yeah.
It's like the shortest part of the ceremony. There's all this other, as you said, there's all this other sort of unbuttoning of the shirt that sort of takes a lot of the time. So
Right, but it is twice as many events with the keying material because you're asking to sign over two instances of the key.
yeah.
Okay.
Yeah.
Hi, Robert Martin from PCH.
Hi, Robert.
Sorry, this bothered me a little. Who decides when to roll back if that's what is chosen to be done? Is that something VeriSign does, or has it been decided who decides?
It's something that VeriSign and ICANN would decide together. The root zone management partners would decide. Yeah, I mean, if you need a list of organizations, but certainly, during that time, we'll be looking for, feedback from users and community. So we're not operating in a vacuum, if that's what you're referring to.
Maybe. Yeah, no, I mean, it still sounds like you don't say, it's Steve Crocker, for instance, that has to press the red button. No, it's still a little bit vague. I'm wondering if it needs to be maybe written down before you do all these things.
Written down, where would you like to see it written down?
Decided beforehand who has to actually who has the final word, because if VeriSign and ICANN disagrees, what are you going to do? Well, okay.
I have faith that, we work closely with these people, and I have faith that something like that would not happen. And so it is written down. I didn't share all of the details with you today. I tried to keep it high level, a little bit short, but there are more details that we have internally.
Okay.
So, yeah, we have given a little more thought than maybe was expressed on these slides.
Oh, that's okay. Okay, thank you.
Dns Oarc Internet Society. First of all, I want to commend you all on doing this work. I think for a number of reasons, getting rid of that 1024-bit key there would be wonderful. We have that as a critique against DNSSEC sometimes, is that there's a lot of 1024-bit RSA still floating around, so anything we can do to get rid of it is good from that perspective. But I actually, Robert asked the question I was wondering about, which was, first of all, when you talk about this and, in the fallback plan, et cetera, how are you planning to monitor to know that there is a problem? And then I guess really it's that combination of the question that Robert asked, which is, how do you decide when something is bad enough to merit going back? So I realize you have more plans, but I guess I'm curious about the monitoring part of that. And then the second part is, I guess, just another vote for more info about how you think about making that back.
Okay, sure. So, regarding monitoring, I think, we're going to use every channel that's available to us. We're going to be watching mailing lists, social media. As we get closer to the event, we'll be publishing contact information where people could, write to us or call us or something like that to report problems. So, again, we're aware of the need for that kind of activity to happen. Yeah.
Okay, I'll just say I think there are a number of us who would be willing to certainly help with that too, or help with the publicity around that. Yeah. I also don't know that I ever saw shirt unbuttoning on the KSK script. I'm not really sure we want that, but
well, you should go.
Matt Poundset from Brightside. I have kind of a data point related to concerns about fragmentation with the larger response. At a certain previous employer where we operated a large-ish and fairly busy TLD, we were signing it with an appliance that has some odd behaviors. It, for one thing, always pre-publishes both the ZSK and the KSK. So there are always 4 keys in the zone. The particularly odd behavior that it has, though, is that it signs the key set with both KSKs and the active ZSK. So there are always 3 RR SIGs in the DNS key response. And the result is that the response is 1,625 bytes, I think. And it's been this way since 2010. Mm-hmm. And as far as I know, there's never been a complaint about somebody having issues resolving the zone.
Yeah. Excellent. Thank you.
Hi, Dwayne. Oliver from Cloudflare. I'm going to ask you a question that you did not cover in this presentation. When will net and com go to the same size zone signing keys?
I have no data on that. I have no schedule. So I'll take it back and we'll,
We'll wait. Okay.
Yeah. I mean.
Yeah.
I don't have anything that I can tell you right now, so, but we'll take it back and talk about when we can talk more about that. Okay. We'll talk about talking.
Follow-up question. What is the rollover plan for the zone signing key now that is big and doesn't need to be rolled as often as a 1024-bit key? Is it basically going to be stable for a few years?
Well, the rollback schedule will stay the same. It'll still be rolled every quarter. Even if it's a 2040-bit key, it'll be rolled every quarter. That's not going to change.
Even during the KSK rollover?
Well, the KSK rollover is designed to, you've probably read the document, but it has periods of activity which are designed to avoid these quarter boundaries, right? So care is taken to avoid blowing up the response size. Okay. Yeah. Jeff will probably talk about that later.
Yeah, later.
Yeah.
I take it the critical point is 1139 octets, which is the size of the DNS key response. And that happens once every quarter when you've got 2 ZSKs in the thing, right? Have you actually done any measurements at 1139? Because I have been, and it's kind of a bit of a worry. I just wondered if you have.
I haven't, no.
Okay.
Not yet.
But do you want someone to look at this hard? We're finding a lot of trouble with basically EDNS 0 being set quite low, and then they're pushing them into TCP. But when you push resolvers into TCP, a lot of them resist that push, either because of middleware or something else going on.
Yeah. Well,
you haven't looked hard at this point.
Okay. We can talk more about it. I mean,
sure.
as Matt said, you would think that if there was a problem, we would have heard about it.
The apocryphal evidence of .org says there is no upper
Right.
limit. Things just work.
Right.
That's apocryphal. When you actually push resolvers into this, you see a subtly different and very, very messy story. And I'm amazed .org actually worked across that period, but it evidently did. So, yeah, you haven't actually looked at this point. Okay.
Right.
Hi, Paul Houders. Just a quick note. Thanks for doing this before the KSK rollover, because just to point it out, it's really important. One of the reasons to do the KSK rollover was to see if there's ever an emergency, can we do this quickly? And the original plan sort of seemed to be, let's first do the KSK rollover, and then we're going to increase the ZSK. And then we again were in a situation where we didn't know if we could do an emergency rollover. So by changing the order and doing the ZSK first, I think it's actually a really good idea so that we can do the KSK rollover, and then afterwards you actually know we can do an emergency rollover. So thank you.
Yeah, all right, thank you. All right, thanks.
Okay, I think we are done for this. I don't know if Keith, do you have any announcements?
Okay, we're breaking for lunch. We will, we're breaking 10 minutes early, but we will resume at 2 p.m. as per the agenda. Usual lunch points, please wear your badge. It's in the restaurant upstairs where we had lunch and social yesterday. Again, if you get any questions about dietary requirements, then speak to Dinesh. You can provide clarity. Thank you all. We'll be back at 2 p.m.